Hello and welcome to the lectures on state space approach to control system analysis and design. In this week, we are discussing the case study of a nuclear reactor. And the topic of discussion in this lecture video is the linear output feedback control. Prior to this, we have seen nonlinear model, we have seen linear model, we have analyzed the equilibrium of the system, we have analyzed the stability, controllability and observability characteristics of the system. We found that the system is unstable. However, it is controllable and observable, meaning that controllers and observers or estimators can be designed to get good response characteristics from the system. And then we did some simulation exercises to understand the transient behavior of the system. In not all representative transients, nevertheless in few transient situations. Now we proceed ahead, and the focus of this lecture is design of a linear output feedback control of this form. U is a gain G times Y plus reference RT. And then so we will design G, we will obtain a G here, and then we will simulate the nonlinear system with this control just to see whether the system, closed loop system with this linear output feedback control, whether nonlinear system has stability and good transient response characteristics. We will simulate and find out. So just a recap of, we have these 5 equations. This is for neutron density, this is for delayed neutron concentration, this is for linear voltage, this is for rate voltage, that intermediate stage VR bar, rate voltage is actually VR, and then the control rod position. We have these 2 algebraic equations and we have parameter values. We linearized the model, and the steady state condition around which the model was linearized is given by these values of various variables. This is the linear model which we obtained. These all derivations were done in the preceding lecture. So we get the 5th order model. Even though the nonlinear model had that product, here it is not the product, this term has separated. So we get this linear model, 5th order model, unstable, however controllable and observable, and those 2 algebraic equations convert into corresponding algebraic equation between the incremental variables delta rho and delta H, delta VR bar and delta Vn. Now given this linear model, these 5 equations, by choosing these state variables, we obtained this state space representation. We indicated this in the previous lecture as well. This is the output and this is the input. Now this is a recap of the preceding. Again the recap, this is the A, B and C matrices in the linear state space representation of the nuclear reactor. So we found that it has 2 eigenvalues at origin, 3 are in the left half S plane, but because of these 2 the system is unstable, and we had established controllability and observability. Of course, eta 0 should be greater than 0 in that condition. For eta 0 equal to 0, the system is uncontrollable and unobservable. This is all established. Now we want to obtain a G in this linear control law, U equal to Gy plus R being the reference, and because there are 2 outputs, so there are 2 elements in G indicated as G1 and G2. G1 is the gain corresponding to the linear output, linear voltage output, and G2 corresponding to the rate output. So we have to obtain G1 and G2 so as to, first and foremost, the resulting closed loop system should have stability and good transient response. And remember, in one of the lectures when we started the case study of nuclear reactor, I had given the control requirements. We should see that we meet those control requirements. So, stability, good transient response characteristics, and we don't exceed the limits on various variables which was stated in the control requirements. Now, if we substitute this G, that means AC, these all elements here are identical to elements of A. These are also identical to elements of A. Only these two elements change. So AC has only two elements different from the elements of A. Only those two elements are altered, remaining are unaltered. However, it doesn't mean that the characteristic equation of AC, in that only two of the coefficients will change. Not necessary. Two elements of A changing doesn't translate to that two coefficients of the characteristic polynomial will be altered. Neither it means that only two eigenvalues could be altered. But let us see what happens, at least numerically. So what we do is, now with that closed loop system matrix, we try to find out the eigenvalues for various combinations of G1 and G2. This has to be done to decide upon a proper G1 and G2. Few of them we will see in this lecture. So first we set G2 equal to 0, and we have various values of G1 in the range from 0 to minus 30. And we look at the eigenvalues and we see these important outcomes. One is that largest eigenvalue, remember, open loop system has two at the origin, one at very close to origin, one relatively away, and one very far, that minus 650, minus 10, minus 0.5 and 0, 0. So this one changes in a very small range, almost unchanged. This minus 10 changes up to minus 9.5, again very small change. This doesn't at all change. It remains always at 0.5. And the remaining two which were at the origin, they undergo change as shown here by this plot. So for this combination of gains, we find that this is for G1 equal to 0, G2 was anyway taken 0 for all values of G1. G1 is 0, they are here, and as G1 increases, increasing G1, the eigenvalues, they go split and go this way, and they meet on the real axis at this point for G1 equal to minus 3, and then again one breaks in this direction, other breaks in this direction. This one reaches up to minus 0.08, and this one keeps going to infinity. So this is the way this eigenvalue, that pair behaves. That means if we change G1, we can stabilize the reactor for G1 greater than 0 and G2 equal to 0. It is possible to stabilize the reactor. Now we see for the other way around, G1 0 and G2 pairing, we consider a large range from 0 to minus 100, and we see that again this largest eigenvalue which was in the left is almost invariant, doesn't vary with G2 also. The one which was close to the origin, probably that is varying. This one eigenvalue remains 0 all the time, and two eigenvalues, that the open loop one was at -5 and one was at -10, they behave like this. So for G2 equal to 0, this is at -0.5, and at -10, this is -10, this is G2 equal to 0. As G2 increases, they travel in this manner opposite to each other. They meet here at this point and then they break away for increasing G2 in this direction. This is G2 increasing. So this is how it behaves with G2. Now what we do is we investigate with G2 equal to 1 and G1 between -7.5 to -20, and we see that this undergoes a small change. There is another eigenvalue showing a small change, another one showing a small range of change, and two behaving in this manner. This is for G2 equal to 1 and G1 equal to -7.5 to 20. So this one is -0.0486 plus j.035. This one is correspondingly -0.0486 minus j.035. For G1 equal to 20, it is -0.869 minus j.044, and this one -0.869 plus j.044. This is for G2 equal to 1, G1 equal to -20, and this is for G2 equal to 1 and G1 equal to -7.5. So this is how it behaves. Now we do a similar exercise for G2 equal to 2, and in this again we see that three eigenvalues on the real axis, they show little variation, and one pair behaves like this. So this is for G2 equal to 2 and G1 equal to -7.5 to 20. So here this one is -0.0456 plus 0.0128, that is the imaginary part. This is for G1 equal to 7.5. This is correspondingly the negative counterpart of that, and this side is 0.074 plus minus j034, this and this one. This is for G1 equal to -20 and G2 equal to 2 in both the cases. So we obtain this one. Now if we change G2 slightly to 2.5 and G1 keep in the same range, the characteristics are almost similar, but it helps us to understand that as G2 is increased, the effect is here 0.047 plus minus j.058. This one is anyway in the left side, so this is important. This decides the characteristics of the system when the system is trying to approach the equilibrium, or these are the dominant pair of eigenvalues when we consider various G1 and G2. These are in previous combination, this one, and so on. So in all the combinations we see that they are of the order of 0.045 or around that, meaning that we can select a G1 and G2 of like this, minus 10 and minus 2.5. I don't say that this is the best design. Nevertheless, based on those characteristics of roots, we select this one for further approaching to time response analysis of the system. Analyze the transient behavior of the closed loop system. The system is initially at steady state. A step disturbance of 5 volt is introduced at the input at t equal to 0. At t equal to 1, the disturbance is removed. So it's like a pulse. And for the first 5 seconds, this disturbance was there for 1 second. Up to 5 seconds, we have the controller off. Closed loop control, we have assumed that controller is off, and at 5 seconds only the closed loop controller becomes active. So the system is under the influence of disturbance as an autonomous system for 5 seconds. Subsequently, it is under the output feedback control with values of G1 and G2, which I showed in the previous slide. So this is the input variation, that first second, subsequently no input, autonomous, and then here the closed loop control switched on. So this is the variation of that u equal to gx, gy, sorry, u equal to gy with that values of g. This is how the input varied. This is the control rod position. So initially when voltage was constant 0.5 volt, the control rod traveled out by this small magnitude, 0.2%. It stayed there for 5 seconds and then it was maneuvered depending upon the control voltage, the feedback signal. This is the change in neutron density. Up to 5 seconds we had the disturbance, we had 1 second, and then autonomous for next 4 seconds. So this is the variation, sorry, here up to here. Then this is from here it is being controlled and the control is trying to bring it to 0. Eventually it will become, deviation will become 0 as t tends to infinity. You see, it is asymptotically approaching 0. This is the linear voltage delta Vn. These two follows the same trend as the neutron density. They are proportional to each other. This is the rate. The rate picks up and subsequently it comes close to 0 and eventually it will become 0 as t tends to infinity asymptotically. So this is how the closed loop system behaves. We see that the system is stable and it has good response. The voltages do not approach that 10 volt which we had stated in the control requirements. So rate is well under control, positive side as well as negative side. So that shows the efficacy of the design. I don't say that this is the best design. One can do a better design than this, but typically the response will come something like this. So thank you very much. We have seen the effect of output feedback control in controlling the nuclear reactor. Thank you very much.